This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 5, Lesson 6, Vibrating Systems, Part 2, Forced Response. Lesson 5 found the natural frequency a system rings at on its own. Now we drive it. One number governs everything, the frequency ratio, R, the drive frequency over the natural frequency. Near R equals 1, the amplitude explodes, resonance. Push R past root 2 and a soft mount isolates the machine from its floor. We build the magnification factor, the phase, transmissibility, rotating unbalance, and the vibration absorber, then size an isolator, 2 ways. Concept 1. Forced response. Drive a spring mass damper with a harmonic force, and it answers at the drive frequency, with an amplitude set by the magnification factor, 1 over the root of a denominator built from the frequency ratio and the damping. At resonance, R equals 1, the first term vanishes, and the magnification collapses to 1 over 2 zeta. So only damping caps the peak. Below resonance, the mass follows the force. Near it, it blows up. Above it, the mass can't keep pace. Concept 2. Phase. The response also lags the force. Well below resonance, the lag is small, and the mass moves nearly in step. Exactly at resonance, the lag is 90 degrees, no matter the damping. The cleanest tell that you are at R equals 1. Well above resonance, the lag approaches 180, and the mass moves opposite the drive. Concept 3. Transmissibility and isolation. Now ask how much force actually reaches the floor. That ratio, transmissibility, crosses 1 at R equals root 2 for every damping value. Below root 2, a mount makes things worse. Above it, you get real isolation. So you isolate by softening the mount, dropping the natural frequency to raise R. And past root 2, lighter damping isolates better. Base excitation gives the identical ratio with the driving term Ky. Concept 4. Rotating unbalance. A rotor whose mass sits off the spin axis throws a force that grows with frequency squared, so its response carries an R squared on top. The denominator is the same as forced response, but that R squared makes the curve climb from 0 and flatten to 1 at high speed. Watch the symbols. Here, capital M is the total mass, not the magnification factor from 2 slides ago. Concept 5. 3 more tools on the same page. A vibration absorber is a second spring mass tuned so its own natural frequency matches the drive. At that frequency, the main mass goes still, and the absorber takes the whole motion. Dunkerley's equation combines several masses on a shaft into one critical speed by summing reciprocal squares. And the viscous damping force is simply the damping constant times velocity. Setup. A 200 kilogram machine runs at 1200 RPM, lightly damped. Part A puts it on stiff mounts. We want the frequency ratio, the displacement magnification, the phase, and the fraction of force transmitted. Part B swaps in softer mounts and asks for the new transmissibility and how much isolation we bought. Everything is in SI, and the forcing frequency is 2 pi n over 60. Solve. Part A. The drive is about 126. The stiff mount gives a natural frequency of 100, so R is 1.26, below root 2. The magnification is about 1.6, the phase past 90 degrees toward 180, and the transmissibility is 1.63. Below root 2, this mount amplifies. It passes more force than a rigid bolt would. A stiff isolator is no isolator. Solve Part B. Soften the mount 4-fold, and the natural frequency drops to 50, pushing R to 2.5, now past root 2. Transmissibility falls to about 0.21, so 79% of the force is blocked. Same machine, same speed. Lowering the stiffness moved R across root 2 and turned a force amplifier into a good isolator. That crossover is the whole game. Traps. 5 ways this bites. 1. R is drive over natural. Resonance at 1, isolation only past root 2. 2. Below that crossover amount amplifies, so stiffer is usually worse, soften to isolate. 3. Damping caps the resonance peak, but hurts isolation above root 2. 4. It is the whole group 2 zeta R squared, added to 1 minus R squared squared, not R. 5. Rotating unbalance carries an r squared on top, so don't reuse the plain magnification factor for it. Quick recall. Magnification, phase, transmissibility, and unbalance all share one denominator, the root of 1 minus r squared squared plus 2 zeta r squared, and only the numerator changes. The response peaks at r equals 1. Force isolation needs r past root 2. A tuned absorber can null the main mass entirely. Golden rule. Everything hangs on the frequency ratio, and damping only trims the peak. Next up, Topic 7. Beams, trusses, and frames. We can predict how a machine vibrates. Now it has to be held up. Lesson 7 returns to statics, sum of forces, and sum of moments to 0, and the method of joints for a loaded truss. Everything is at peprepengine.com. Cheat sheet, work solution, and a quiz attached here. If the course helps, subscribe.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.